All right, so we've talked about quadratics in standard form, and now we're going to talk about quadratics in vertex form. And these are actually even easier than quadratics in standard form. It relates to some things that we've already done before. So the first thing I want you to know is the parent function is just f of x equals x squared. Remember, this is just the most basic form of any specific function family. So this is x squared, remember, reminds us that we're going to be looking at the parabola shape, which is that kind of U shape. So the first thing I want to do is just show you what the parent function looks like and some characteristics of it so that we can see how to apply that to some other transformations. So if we look at the table of values, if I look at the value -2, if I do -2 squared, that's going to give me +4. -1 squared is going to give me 1. 0 is going to give me 0. 1 squared will give me 1. So notice, first of all, this is turning around. So I've got this vertex point here in the middle. So 0, 0 is the common vertex for the parent function. 2 squared is 4, 3 squared is 9, 4 squared is 16. And so we've already talked about this, that we've got this kind of matching pattern on each side when we do parabolas. That's what makes them that U shape. But what I want to show you is there's a specific pattern in how these change. So from the vertex, and I'm just going to move one direction even though this works both ways, notice that this is going +1, +3, +5, +7. So what I want you to see is, one, this is not linear because this is changing by a different rate every time, but there is a pattern here. This is actually adding odd numbers every time. So when I graph, I'm going to zoom in so you can see it. I'm going to start at my vertex, which is at 0, 0, and the parent function is going to say, go up 1 over 1, and we're going to go both directions so we make the parabola. Now it's going to go up 3 over 1, both directions. And then up 5 over 1, ran out of room there. And if I had room, I'd go up 7 over 1. And that's what's going to create this curve on both sides. So the pattern that you want to write down is this 1, 3, 5, 7 over 1. All right, and that's because I write it over 1 because notice I'm always going over 1, and we want to treat this kind of like a slope, kind of like a rise over run situation, and that's how we're going to use this today. So let's look at how to apply transformations to that. All right, so what I'm going to do is two very similar problems, one that's absolute value, which we've already talked about before, and one that's quadratic. So there are going to be a lot of similarities in these, but there's also going to be some differences just in this general shape that they make. So if we look at this absolute value, if you remember our dance moves, inside's the opposite and outside's the same. So the first thing we would do is name the vertex, 3, -5, and we would go ahead and plot that because that's our starting point. And remember, in absolute value, that these are going to be in a V-shaped graph. The other thing we would use is the slope, and we would say this slope on the outside is 2 over 1. And that's because a regular slope is just 1 over 1, and we're multiplying the top number by 2 because it says to multiply by 2. So we're going to go up 2 over 1, up 2 over 1. We'll do that a few times, and then a few times on the other side, up 2 over 1. And then this is going to make this V-shaped graph here. And then if we talk about it, domain is still going to be all real numbers, and range is going to be y greater than or equal to -5. Now let's see how this is similar, but a little bit different when we talk about quadratics. Okay, so in our quadratic over here, we're still going to do the same idea. Inside's the opposite, outside's the same, so that's going to make my vertex at 3, -5. So that's where my first point is going to be, 3, -5. This time, remember that the general pattern or slope for x squared is going to be 1, 3, 5, 7 over 1. Now, this outside number, think about it. On the outside, we shake our head up and down. So we've talked about this a little bit before, but I haven't stressed it too much. Since we're moving our head up and down, that's a vertical direction. And we're also telling ourselves, yes, that it's the same. So the way I process that is vertical. I keep that number the same, which is 2. And because 2 is bigger than 1, this is going to be a stretch. Now, because I'm changing the vertical component in this pattern, look down here, in this pattern, rise is the vertical component because rise is when you move up and down. Run would be horizontal. you all are only ever going to deal with vertical this year, so we're going to change this by a factor of 2. And what that's going to do, instead of going up 1 over 1, I'm going to go up 2 over 1, and I'll even write this out. I'm going to go up 2 over 1, up, and I should probably write it like this, up 2 over 1, up 6 over 1, up 10 over 1, and up 14 if I had the room. So notice I'm just multiplying the top numbers, not the bottom numbers, so the run is still 1. So again, when I graph that, I'll zoom in here. I'm going to go up 2 over 1 on both sides, up 6 over 1 on both sides, and then if I had room, I would go up 10 over 1 next. All right, and that's going to create this graph right here. And then when I go to name, domain, and range, again, that's going to be very similar. Domain is going to be all real numbers, and range is going to be y is greater than or equal to -5. So notice that you learned before that there were some shortcuts for naming the range, right? We could look at the outside number to see if it was opening up or down, and look at the y part of the vertex to see what the y part of the range was. Notice these graphs look pretty similar, except for that obviously one is a U shape and one is a strict V shape. All right, and then the last thing that I want to tell you is that if we were to name transformations, they would be the same for both of these. So if we were actually going to name transformations out in words, because you'll see this on your assignment, they would be right 3 or a shift right 3. They would be a shift down 5. And then again, we call that 2 on the outside. We call that a vertical stretch of 2. All right, let's look at 1 or 2 more examples. Okay, so these last 2 examples are still vertex form, even though they may not look like it. So this right here, when you see vertex form, generally you recognize it because you've got the parentheses. And this one has parentheses missing. Well, they are really there. They're right here where the x is. So another way to write this would be -3 x plus 0 if you want to do that, since there's nothing in there. And then the plus 6 on the outside. So if I do that, that's going to give me a vertex of 0, 6. Which I can go ahead and plot. And then I know my pattern, my normal x squared pattern is going to be 1, 3, 5, 7 over 1. And what I want to do is do a vertical stretch by -3 on the top. So I'm going to multiply this top by -3. That means I'm going to be going down 3, down 9, down 15, down 21. So I'm going to go ahead and do that now. Down 3 over 1. Down 9 over 1. And usually you're not going to be able to fit a ton of points because when we stretch them, you start counting by such big numbers. And we just want to draw this to make it look as much like a U as possible. So when we name the transformations, I get that we have a shift up of 6, a reflection, that's the negative out there in the front, and a vertical stretch of 3. So remember, you should be good at naming those transformations. I think you all are pretty good on domain and range, but I can do that again one more time just for practice, right? Domain is all real numbers. My range this time is going to be y is less than or equal to, because I'm opening down, +6. And the only other thing that you might be asked to do from vertex form, which you should be able to do anyway, is to name the axis of symmetry. Remember, the axis of symmetry goes through the x part of the vertex right here. So if I'm going to name the axis of symmetry, I can just name it x equals 0. Whatever the 0 part of the vertex is going to be your axis of symmetry. All right, let's look at one more. Okay, so this one, same thing. Name the vertex. Inside's the opposite. Outside's the same. Since there's nothing on the outside, that's just +0. You're welcome to write +0 if you want, or just know that it is 0. My general x squared pattern is 1, 3, 5, 7 over 1. This time I have a 1/2 on the outside, so it's still vertical. I'm multiplying by 1/2. Because that's less than 1, we're going to call that a compression. So it's still vertical, but we call it a vertical compression of 1/2 because it's going to make it shorter, not taller. So if I go ahead and graph this, -5, 0. Let's see, get that plotted. This time I'm going to be going up 1/2 over 1. So I'm going to zoom in so you can kind of see me do this. All right, I'm going to go up a half and over 1, so still going over a whole count, just only up a half. Now I'm going to go up 3 halves, 1, 2, 3 halves over 1. Same thing on the other side. Now 5 halves, 1, 2, 3, 4, 5 halves over 1. And then up 7 halves, 2, 3, 4, 5, 6, 7 halves over 1. So notice you still go over 1 every time. It just changes how far up you go, and that's going to be symmetrical on both sides. You should not see anything other than x squared, because the other fractions get a little bit too complicated to count by unless the graph is just set up really well for you. All right, so that's what this one looks like. Again, if we were to practice naming domain and range, domain's all real numbers. Range is going to be y is greater than or equal to 0, because that's the lowest y value. And then if we name the axis of symmetry, that is going to be x equals -5. If you haven't already noticed, the range matches the y value from the vertex, and the axis of symmetry matches the x value from the vertex.